All right, today we're going to dive into something really cool from the world of computer science. It's kind of like a brilliant shortcut, a way to prove that really complex systems are safe without getting totally lost in an infinite maze of possibilities. We're going to see how one small, clever change in the rules of logic can have an absolutely massive impact.
I mean, think about it. This is a question that must keep engineers up at night. When you're talking about systems where failure just isn't an option, flight controls, medical equipment, the power grid, you need absolute, rock-solid certainty. But how on earth do you mathematically prove that a system will always do what it's supposed to, when there are literally trillions of possible states it could be in? And that right there is the heart of the verification challenge. To get that level of certainty, computer scientists use these special languages called temporal logics. You can think of them as a way to write rules not just about what a system does, but when it does it and in what specific order. For a long, long time, the undisputed king of these logics was something called CTL Star, or CTL Star. It's the gold standard because, honestly, it's incredibly powerful. It can describe pretty much any system behavior you can dream up. But all that power comes at a steep price. Using CTL Star to actually check a system can be so computationally expensive, it's like trying to count every single grain of sand on a beach. You just can't. But this is where our story gets really interesting. To get around these massive hurdles with CTL Star, researchers came up with something called Bundled CTL Star, or BCTL Star. And here's the key part. It's not a weaker version. It's a smarter one. It has almost all the expressive power of its big brother, but it's way, way more efficient to work with. So what is BCTL? At its core, it's a type of logic that takes a different approach. Instead of trying to analyze every single tangled possible path a system could ever take, it focuses on a curated or bundled set of the most important ones. This little redefinition of what counts as a path, well, that's the whole secret. Yep, this redefinition is the secret sauce. The genius of BCTL isn't about adding new, complicated features. It's about establishing a couple of very specific, very clever, and just slightly more relaxed rules for what counts as a valid path for a system to follow. To really get your head around these bundled paths, let's use an analogy. Imagine you need to verify a massive railway network. The old way, CTL, is like trying to analyze every single possible journey a train could ever make by switching tracks whenever it wants. It's totally exhaustive, sure, but it's just overwhelming. BCTL, on the other hand, is like being handed the official train timetable. You're only looking at the approved routes. It's a much smaller, more manageable set, but it still represents all the essential, valid journeys that can actually happen. And this timetable operates on two really simple, common-sense principles. First up is suffix closure. All this means is that if the journey from London to Edinburgh is on the timetable, then the shorter trip from, say, York to Edinburgh is also approved. Makes perfect sense, right? Second, you have fusion closure. If there's an approved route from London to York and another one from York to Glasgow, you can fuse them together to create a valid London to Glasgow trip. It's just intuitive. So the million-dollar question is, what did they leave out to make this work? BCTL Star very strategically drops a rule from CTL Star called limit closure. Now, this is a tricky one, but it basically says that if you have an infinite number of little pieces of valid journeys, then putting them all together into one infinite journey must also be valid. By letting go of that really strict requirement, BCTL Star simplifies things immensely. And this isn't a bug or weakness, it is the core feature that makes it all work. Okay, so what's the big payoff for this clever bit of simplification? Well, in computer science, it's massive. It's the difference between having a problem that your computer might literally never finish solving and one where you are guaranteed to get a concrete answer. Let's just look at the old way for a second. A really common thing you need to prove is fairness, like making sure every user who's waiting for a printer eventually gets their turn. With CTL, trying to verify that kind of fairness property is an absolute nightmare. The problem is so hard that computer scientists have a name for it, 2xTMP complete, which is basically code for don't even bother trying. And this is exactly where BCTL shines. First, and most importantly, it's decidable. That means you are always going to get a clear yes or no answer from your program. Second, because it's simpler, it lets you use more straightforward methods for automated proofs. And the real kicker, it handles those super tricky fairness problems much, much more efficiently. Let me put that into perspective for you. A 2exp time problem gets impossibly slow, incredibly fast. We're talking about computer runtimes that could theoretically last longer than the age of the universe. No joke. BCTL, by keeping the problem within what's called EXP time, brings it back from the realm of the impossible to something a powerful computer can actually get done. It is a total game changer.
What's really cool is that this idea of bundling wasn't just some one-off trick for one specific problem. It actually created ripples, influencing how people designed other kinds of logic all across computer science.
So, like we've seen, its biggest and most immediate impact was making fairness verification actually practical. By dropping that one strict rule, BTL Star found the perfect sweet spot. It was still powerful enough to express the kinds of fairness we care about, but simple enough for automated tools to handle without melting down.
And then the idea started to spread. It popped up in so-called robustness logics. These are systems designed to prove a program won't break when it's under stress. The techniques and proof methods that were pioneered for BCTL became a kind of blueprint for these new logics, like robCTL.
And it didn't stop there. The concept of bundling even made its way into the worlds of AI and game theory. Logics that have to reason about the strategies of multiple different players, like in a really complex game, also adopted this approach. It gave them much more efficient ways to figure out what the outcomes could be.
So, if we're going to sum this all up, this quote really just nails it. The power of DCTL doesn't come from being bigger or more complicated. Its power comes from a subtle, incredibly intelligent change to its underlying model, a small tweak to the rules that ends up having massive practical consequences.
And that leaves us with a pretty fascinating thought to end on. BCTL teaches us a powerful lesson. Sometimes the most elegant solution isn't about building a more powerful engine, but about choosing a smarter map. It really makes you wonder, doesn't it? What other incredibly complex problems are out there, just waiting for a solution that comes not from adding more stuff, but from cleverly and courageously redefining the rules of the game?